right, so this video is going to talk about the fundamentals of hypothesis testing. And in particular, we're going to look at hypothesis testing as related to a single group, a single mean. Okay, so what is hypothesis testing? It's a scientific procedure that enables a researcher to decide whether to accept or reject a statement about the relationship between two variables. So that's really the whole point. We're trying to determine whether or not a relationship actually exists between two variables. Usually in an experimental context, that's the independent variable and the dependent variable. Now the process is pretty straightforward. We're going to ask a research question of interest, and we're going to make a prediction about the answer to that question. Now the prediction is in fact the hypothesis, and we really break down the prediction into two kinds of hypotheses. The first is called the null hypothesis, and the second is called the alternative hypothesis or the research hypothesis. We then collect sample data, and then we're going to analyze that data. We're going to evaluate the hypothesis, and we make a decision to either reject or fail to reject the null hypothesis. The null hypothesis is what we actually test. And then we take those results and we generalize back to the population. We look to see if there are any research design issues. Maybe we want to address some of those in our next experiment. Okay, so the important thing to know about the null hypothesis and the alternative hypothesis is that they are competing hypotheses that are mutually exclusive. So they're formal statements made with notation, and we'll get into that in just a moment. Only one of them can be true. And so let's start with the null hypothesis. Typically that's notated in textbooks as H sub 0. And the null hypothesis is what we test. Okay, we're going to test the validity of the null hypothesis and whether or not the null hypothesis makes sense given our data. And again, it's a statement that there is no relationship between two variables. Okay, so that's the most important thing to remember just for now. It's simply a statement that there is no relationship between two variables, and that's why it's called the null hypothesis, that there is simply zero relationship. Now, the alternative hypothesis is sometimes called the research hypothesis, and in different textbooks, it's either notated as H sub 1 or H sub A. And this is kind of what we're most interested in, right? It's the research hypothesis of interest, but we never test it directly. Okay, we never test the alternative hypothesis directly. Instead, what we test is the null hypothesis. And the alternative hypothesis is a statement that there is a relationship between two variables. Okay, so it sounds a little abstract, I know. So let's walk through an example that might help make this make a little bit more sense. Imagine we are interested in the effect of using online videos to learn statistics. Sounds kind of familiar, right? Now, we already have data from final exams from several past traditional classroom courses. So we know how students have done in the past. Now, the question is the difference in the sample mean and the population means more than what we would expect simply by chance? Well, you might want to ask, well, what do we mean by the sample mean and the population mean here? Well, we're going to define the population as students who have taken a traditional statistics course at a college. Okay, so we have the mean for them. We have a standard deviation of their scores. And really then, the sample is also going to be a group of students who take a statistics course from a college, but they're going to be a little bit different in that they're taking an online course using videos. So that's going to be our sample. So they're clearly a little different in terms of the mode of administration, but they're all students who took a statistics course. And the question we're going to ask is whether or not the students in the online course had a different mean score on the final exam than the students who took the traditional course. Okay, so what do we mean by chance? Okay, chance in a statistical sense is a pretty straightforward concept. Okay, and really it's the answer to this question. Could any difference between the sample mean and the population mean be accounted for by sampling error, right? Because, if sampling error could account for the difference, then we'd be really pretty reluctant to say that there was an effect for an intervention or an experimental effect. And we know from past things that we've learned that sample means will not exactly equal population means. That's just the nature of sampling, right? So there's going to be a difference between the sample mean and the population mean. We just want to know if the magnitude of the difference between the sample mean and the population mean is so large that it's unlikely to be due to sampling error. So is the difference between the sample mean from the population mean more than what we would expect because of sampling error? So then, of course, the question is well, how do we calculate the average amount of sampling error we would expect for a given sample size? Well, here's the good news. You already know how to do that, right? Because that is the standard error of the mean. And to refresh, the standard error of the mean is expressed in this formula. It's simply the population standard deviation divided by square root of n. When we don't have the population standard deviation, right, we need to estimate that. Okay, so let's take a look at the data that we have. Okay, we have a population. This is historical data from prior courses. And the mu here is 78.13 and sigma is 8.24. So we collected all the scores from all the old final exams, and the mean was 78.13, standard deviation of 8.24. Now, we then ran a class where they used online videos, right? We'll call that our sample. Okay, so they're using online videos, and let's say that they ended up with a sample mean of 81.22, a sample standard deviation of 7.34, and an N of 36. So there were 36 students in that class. Okay, so really, what we're really interested in are these numbers right here. We know just by looking at the two means that the mean for the students taking the online videos was a little bit higher, but we don't know if it was so much higher that we could say, hey, it was probably due to the videos, or could it have just been due to sampling error? Okay, so now what we have to do is we have to run a single sample z-test to answer that question. Now, the good news is we are already given the population standard deviation, so we know what the variance is. It's just the square of the standard deviation here, okay? And we're also given the population mean. So under those circumstances, we don't have to do any estimation at all, right? So we already know the population mean, the population standard deviation, and by inference, the population variance. So we can just go ahead and calculate the standard error of the mean. We don't have to worry about the estimated standard error of the mean. Okay, so the first thing that we're going to do now, let's specify the null hypothesis. Now, the null hypothesis would be that there's really no relationship between completing the online videos and test performance. And that would be pretty much the same as saying that the scores on the final exam for students who took the online videos is equal, the mean is equal to the mean for those students who took a regular classroom course. In other words, it didn't matter, right? It didn't matter at all. Okay, whether you had the online videos or whether you were in the classroom, you're going to end up seeing means that are the same. Now, to express that in notation, we could say the same thing by saying, look, the population mean for those students who took the videos is going to be equal to the population mean for those students who took the traditional class. You might say, well, why aren't we using the sample mean here? Well, the reason we're not using sample mean here, right, is because we're trying to draw conclusions about the larger population of students who could have used the videos, right? So we're going to use notation that uses population parameters. Okay, so here's mu for the videos is equal mu for the traditional students, and the null hypothesis is that, hey, those are equal. Those means are equal. We could shorten that and just say, same way of saying it is that the mu for the students who took the online videos or studied with online videos was 78.13, which was the same mu as the students who were in the traditional classroom. And we could shorten it even more, and this is how you typically see it within text, is just that mu equals 78.13. Okay, so the mu for the students who are taking the class using online videos is going to be equal to the mu for the students who went through a traditional classroom setting. So that's the null hypothesis. This is what we're going to be testing, okay? Now, we will specify the alternative hypothesis, and you might expect that it would look something like this, that the means should not be equal. Okay, so the alternative hypothesis, and again, depending on the textbook you're using, it'll either be H sub 1 or H sub A, typically, is expressed a little differently, and it's expressed with this not equal sign. Now, we don't know the direction of the difference, and we're not predicting that. But what we're saying with the alternative hypothesis is that, yeah, there is a difference between the means for our sample and the means for the population. Those means are not equal, and those means and the inequality cannot be accounted for by chance or sampling error. So another way to say this is that the mean for the students who took the class using videos was not 78.13, or to shorten it, mu does not equal 78.13, and that's the way 78.13, and that's typically the way it would be expressed in a textbook. Okay, so let's start by calculating the standard error of the mean. Again, here's our population. Okay, these are the students who took the class in a traditional format. And then we have another group of students who took a stats course, but in a different format. We're just going to call them a sample. Okay, and again, the means are different. We know that already. So now what we have to do is calculate the standard error of the mean. Okay, so there's our formula, and we're just going to plug in the numbers. Right? We have sigma, so we're going to put sigma in there. We also have n, so we're going to put the n right in there and take the square root of it. So that's 8.24 divided by 6 is 1.37. So what does that 1.37 mean? What that means is that given this particular sample size and the amount of variation in the population, we would expect sample means to deviate from the population mean on average 1.37 points. Okay? So let's now go to the next slide. What we have to do now is calculate the z-score for the sample mean. So here's our formula. Okay, we have all the data that we need. Okay, sample mean goes up here in the numerator. Population mean also in the numerator. And then all the action, of course, is happening in the denominator in statistics. And this is our standard error of the mean, which we calculated on the previous slide. So we walk that through, and we get a value of 2.56. So what does that z-score value mean? What that means is, in the sampling distribution represented by the null hypothesis, which is these folks, right, in the population, okay, in the sampling distribution represented by the null hypothesis, the sample mean that we observed for the students taking the online video was 2.56 standard errors above the population mean. So let's take a visual graphic and we'll see what this looks like. So in the sampling distribution, again, the mean for the sampling distribution is going to be the mean for the population, right? So in standard error unit terms, it's simply 0. But in raw score units, it would just be the mean of the population here. This would be the mean of the students who actually took the classroom version of the course. Okay, so we have standard error units here. Okay, and then the question is, where are we going to locate our z-score, right? Now, again, the z-score that we just calculated is in standard error units. So as a result, these numbers are going to perfectly align, right? So when you look at standard error units and z-scores, they're going to be exactly the same spot. Okay, so that's where we're going to put our z, right? So it's about halfway between +2 and +3 standard units, error units. Goes somewhere like right here, okay? And what that means is that there is a relatively small proportion of area under the curve that has values higher than it. And over, if we look at percentiles, right? Over 99% of the area under the curve is lower than it, okay? Okay, so that's where we would locate the z-score. Okay, so then what do we do next? Well, we've done a really nice job up to this point. We found out that, hey, the folks who took the online video version of the course, performed a little bit better on the exam, and it was getting out into kind of outlier region compared to folks who took it through a traditional classroom experience. So we need to make a decision whether or not to reject the null hypothesis. And again, keep in mind, the null hypothesis here is that taking the course using online videos would have no effect, right? There was no relationship on test scores. But we seem to be saying, it kind of looks like there is, right? Otherwise, how do you explain that z-score, which is located out in the tail of the sampling distribution? So what we really mean here is how likely is it that the sample mean would be observed from the sampling distribution that represents the null hypothesis? Is it likely or is it not unlikely? Well, if you have a z-score in the tail, that's pretty unlikely to occur by chance. But we really need a cut point to make that decision, right? We need a cut point that's going to say, okay, do we reject the null hypothesis? We reject the idea that there's no relationship between two variables, or do we fail to reject it? Okay, and that's going to be the question that we're going to be taking up here shortly in the next video. But I want to point out really quickly some caveats to null hypothesis testing. First of all, we never prove anything, okay? Null hypothesis testing is always probabilistic. So we don't prove that something works or that there's no effect or no relationship between two variables. Why? Well, conclusions could change with additional information. So again, remember the standard error of the mean, the size of the standard error of the mean is a function of how big the sample size is. So if we increased our sample size, we make it a little bit more likely that we're going to actually reject the null hypothesis, okay? Because our standard error of the mean gets smaller. Okay, so our conclusions really are conditional on the kind of information that we have, and you can make a strong case many times that if you simply increase the size of the sample, you would increase the likelihood of actually rejecting a null hypothesis. The other thing is that, even though, let's say we did reject the null hypothesis and we said we have enough information here to claim that there's a relationship between two variables, there's always confounds in third variables, and there's design issues that we would have to think about. In the example that we're using here, this is not an experimental design, right? There's no true control group. There was no random assignment of participants to either the online video manipulation or to the in-class traditional presentation. Okay, so it's not a true experimental design. Could be with the students who completed the online videos that there was something different about that sample, right? Maybe these are some go-getters to begin with, and they would have had high scores on the final exam regardless of the way information was presented to them. Another possibility is that with online learning, a lot of the exams are take-homes. And maybe with the traditional classes, their exams were in class, and maybe that accounts for the difference. So even if we did reject the null hypothesis, that doesn't eliminate threats from weak designs, okay? And so you have to take that into account, that you have both the questions about statistics and what the statistics mean, but the statistics will never be any better than your design. If you have a weak design, right, that makes it difficult to really explore or make conclusions about cause and effect and so forth, no statistics in the world are going to fix that. Okay, so in this case, we really don't have an experimental design. It's more of a quasi-experimental design. The other thing is that rejection of the null hypothesis is a statement about the reliability or the likelihood of a result, not its magnitude or importance. Okay, so whenever we reject the null hypothesis, and again, we're going to go over specifically how to do that in a coming video. Whenever we reject the null hypothesis, okay, we're simply making a statement about the likelihood that sampling error or chance could account for the difference between the sample mean and the population mean. Okay, that's all it means. It doesn't tell us how important the result is, why we got the result, or so forth. It's a relatively simple statement about whether or not the difference between the sample mean and the population mean could be accounted for by sampling error. Okay, so the big picture, we start by assuming the null hypothesis is true. H sub 0 is the term that we use for the null hypothesis. H sub 1 is the term we use for the alternative hypothesis. And after calculating the standard error of the mean, we then calculate a z-score for the sample mean and plot it in the sampling distribution for the null hypothesis. Okay, and by sampling distribution for the null hypothesis, we just mean the distribution of means represented by the population, where we assume that there is no relationship between the two variables. In our example, there is no relationship between taking the online videos and test performance, and as a result, we can simply use the distribution of means for students who took the traditional class approach to the course. Now, if the sample mean is far from the mean of the sampling distribution, in other words, there's a large z-score, then maybe the sample is from a different population. In other words, maybe there's something different from our population compared to the rest, or something different for our sample compared to the rest of the population. Okay, and then the next thing we're going to do is we're going to talk a lot more specifically about how to evaluate the null hypothesis. How do we know specifically when to reject or fail to reject the null hypothesis? That's coming in our next video.